All right. Hello, everybody, and welcome to Mobile UI Performance Tips. As mobile hardware has gotten faster and faster, we started to see it pop up in all sorts of new places, cell phones to store kiosks, planes, trains, automobiles. There's never been more opportunities to do cool things in Unreal Engine. So there's never been a better time to talk about performance, because it is critical to keep your project running quick if you want to squeeze out more of those gorgeous visuals. So we're going to be talking about motivation. Why should you care about UI performance on mobile, even if you don't think your project is very UI heavy? We're going to talk profiling. How do you measure performance? How do you tell kind of which techniques you should be using and make educated decisions? I'll share a bunch of optimization techniques to add some tools to your toolbox. And at the end, I've got some miscellaneous tips that didn't really fit in anywhere else, but are worth talking about. But before we do that, we're going to talk about me. My name is Cody Albert. I am on the Tech DevRel team. I've been at Epic for about 8 years now. In that time, I've supported a number of different teams, including UI and the automotive HMI team. So this is sort of a marriage of two topics I care a lot about. And I've got a QR code there if you want to check out my profile on the dev community. I'll post snippets, tutorials, and things like that from time to time. So let's get into it. Motivation. Why is UI performance so important on mobile? Even, as I said, if you don't think your project is very UI heavy. And the biggest thing here is that resources are extremely precious. Very limited draw calls on mobile, especially if you want to support slower hardware. Memory is being shared with other applications, so you want to keep your memory footprint as low as possible. And you want to reduce the CPU cycles you're using to get a good frame rate. Anytime you don't spend on UI, you can spend on 3D visuals. You can make whatever you're showing on screen look a little bit better. And small decisions can have big costs. In terms of draw calls, widget layout can cause something to take more or less draw calls, even if it looks visually identical. Memory can be affected by texture sizes, or there's a lot of trade-offs where you might be caching things for performance, which makes the memory footprint bigger. And CPU cycles, we always see death by 1,000 ticks. Even empty tick nodes can cause a tiny bit of extra performance hit that can add up over time. So the way I see it, there's sort of two different ways that you can approach a project when starting in Unreal. You can stay in your lane and let the designers cook, figure out the budget later, make it an engineering problem, just take the cool mock-ups, get them into the engine, get it going, get a project out the door, and then call up your engineering team and tell them to fix the frame rate. Or you can do it the Unreal way. Implement best practices from design to ship. Make performance a little bit of everyone's problem. Make good decisions from the beginning so that you don't have to call up the engineers later. So we're going to talk about the second one, because that's the Unreal way. And we're going to start with profiling. So how do we measure performance? Originally, when I kind of came up with the concept for this talk, I was just going to kind of give a bunch of techniques, and I figured that would be enough. But they all have trade-offs, and it's hard to understand which techniques to use and when unless you can actually do some A/B testing on your own content. So I wanted to give a little rundown of how to measure performance of your UI, and how to get data off of your mobile devices. And before we get too into the weeds, I think it's important to set your team up for success. Rather than just have the guy at the company that can do the performance profiling, you should build good onboarding documentation from the beginning. Your studio has a very specific environment that you're working with, an IT department that may or may not have limitations on your machines. You may be shipping to specialty hardware. Nobody's really going to know your situation better than you. So I highly recommend, from the beginning, building onboarding documentation, link out to the relevant Epic docs where you can, but make sure you have that document and make sure it's a living document. Whenever somebody joins a project, you give them this document, and their first assignment is to run through it and fix it wherever it's inaccurate or wherever there is missing information. Next up, you should establish a good pipeline for gathering data. And that can be, we'll talk about both these later, but this could be stat slate numbers, just get an idea of how many widgets you have on screen at a time, how long it's taking. And you also want to get some insights captured, so a little deeper data on where your spikes are and where you might need to improve performance. I recommend saving these off, getting a nice history of these things, maybe whenever you release a milestone or at some regular interval, so that when performance goes out the window, you can kind of look back and see where things might have gone wrong and narrow down potential causes. And then if you're feeling a little spicy, you can also automate a lot of these things. We have tools like the CSV profiler and the Studio Telemetry plugin, which you can use to collect data across your whole studio, especially useful for bigger studios where it might be harder to determine exact causes of performance drops. So you can set up these pipelines and start gathering data. So as a quick study on why I think onboarding documentation is so useful, I set up a sample project for this talk, which we'll get into a little later. And I needed to get some insights traces off of it. And I looked around, and I had a little trouble figuring out what to do. And eventually, I found a PDF from somebody else in the studio that had kind of gone through the same thing a couple of years back. It was for 427, updated all the paths. And this is what I ended up needing to do. So this is how you get an insights trace off of Android. You got to save your command line arguments out into a text file. You have to push that to a very specific folder on whatever mobile device you're testing. You have to set up a port reverse with ADB reverse, and then you'll start getting your insights traces. If you miss any of these steps, you just kind of won't, and nothing will happen. So just, because I'm responsible, I published this onto the dev community. So this information is there now, but similarly, when you have to go through this process, it's really worth saving it out somewhere and sharing it with your team. All right, so the two main ways to gather performance information. The quick and dirty first way is stat slate console command. You've probably seen this. There's a couple numbers on here. The first one, you can get frame time, pre-pass tick paint. This was a little volatile on mobile when I tested, so I would take these numbers with a grain of salt and get them from insights instead. But you can get at least like a finger on the pulse to get an idea of how things are going. More importantly, you can get your widget count, how many widgets you have on screen, which is the element count here, and how many of those widgets are ticking. And then you can get your layer count and batch count, which are going to roughly translate to your draw calls caused by your UI. So you can see if that's in the tens, the hundreds, the thousands, and get an idea of where there might be some issues. From there, you're going to want to get insights traces. This is where the real data is going to come from. So when we talk about Slate Insights, I'm referring to Unreal Insights with the Slate Insights plugin enabled. That's going to give you some extra tracks and some extra information on top of the normal Unreal Insights info that you can get. So three big things here. Once you turn on that plugin and turn all the channels on, you'll get the Slate frame info at the top here. That's these lines with a dot. This is for a single frame here, but you'll see it over time, and you'll be able to identify spikes when it's zoomed out. You can click those dots to get the frame view, which we'll show at the next slide. And then we have the update steps here, and then the regular game thread view here. These are sort of two different ways to parse the same information on how long it took to tick your UI. So the normal game thread view is going to give you function names, an idea of which functions are taking a while. The update steps is going to sort of zoom everything out and show just the names of the widgets and how long it took to draw all their children. So this can help you kind of reason about how long different things in your UI are taking, and you might be able to find a very expensive spot to dig in further on. And for that frame info, it's going to be two different things here that are useful. The top here is invalidation debugging. This is really only going to matter if you've enabled invalidation, which I'll talk about in a bit. But it will tell you which widgets invalidated this frame and why they invalidated. So if you have a very expensive frame, this might help you kind of dig into what's going on. Under that, we have the widget updates panel, which just tells you all the widgets that updated this frame, how long they took. And you can see at the bottom there, the window cost 262 widgets to redraw and took 1.5 milliseconds here. This is off Lyra. So that's sort of the all-encompassing view, and we can kind of see which widgets took how much of that time there too. And for a more specific example, I found an expensive frame on Lyra, and I tried to dig in to sort of see what was going on here, and we'll kind of go left to right. So at the very beginning of the tick, we see that there is a sequencer animation that is playing. Can't really see it here, but sequencer is updating some things, which is what this attribute updates is. So we can say that it took about that long for all those attributes to get updated by an animation. Next up, we saw that there was a weapon changed event being fired, and that caused two calls to create widget, one for reticle pistol, one for ammo counter pistol. And from that, I can tell, okay, this is a frame where I switched from the shotgun to the pistol, and it caused an animation to play, created new widgets. That's why this one was more expensive than the ones around it. If I were trying to optimize this, I might, try to cache off these widgets instead of creating them every time, or I might try to clean up this animation to take less time if it were a problem. And just to get a quick idea of what I was working with here, so I built a sample project with a tablet that I tested on. I used a Galaxy Tab S6. This is a 4-year-old tablet with a Snapdragon 855 and 6 gig of RAM. On the HMI team, we'll use this as sort of a stand-in for the 8155. This is a good target, middle-of-the-road platform that we can use to get some performance metrics. And I threw it into Lyra to see how it would do compared to my development machine, which is a fairly beefy machine, 3080. And it is 3 times slower to draw the Lyra HUD. So that's sort of what we're working with on expectations. It took 2.39 milliseconds to draw each frame. And that's a little rough if you're trying to hit 60 FPS and you only have 16 milliseconds to work with, and that's for a pretty basic HUD, but that's about what we can expect here. So on that note, let's go into optimization. How do we improve these numbers? What sort of techniques exist that we can look at that will help here? And to demonstrate some of these, I set up the mobile UI testbed project. So that is this little HUD here. I kind of set up a fake RPG or MMO interface. I stole all the art because I can't draw. That's my dog. And the idea here was that I could sort of test a couple techniques and see what the numbers actually looked like. Big caveat here, this is completely static. So I have a lot on screen. I didn't dive into like animating it and really getting an idea of what that would cost because the data there gets a little more project specific. So this will give you an idea of draw calls based on number of widgets drawn, but animation could be its whole own talk probably. And we're going to talk about 4 animation or optimization techniques here. The first is atlasing, a old school technique of building sprite sheets that is not really worth doing on PC all the time, but potentially super useful on mobile when we want to cut draw calls down. We're going to talk hierarchy design, how we can set up our widget hierarchy to reduce our draw calls. I'll go over retainer panels and when to use them and when not to use them, as well as the invalidation system, which is both global invalidation, enabling it for your entire UI, as well as scoped invalidation through invalidation panels, where you might only want to apply the invalidation system to some subset of your UI. And we'll start with atlasing. So the idea behind atlasing is we take a bunch of textures that we think will appear on screen at the same time. We combine them all into a single texture, and then we can draw segments of that texture on the screen all in one draw call in some situations. So the pros here are a single draw call for a lot of different textures, as well as preloading. This is a single texture that we load at one point. So once it's loaded, we're going to have very quick access to all of these bits from it. The cons are there is some setup involved here. You have to create a sprite sheet. There's tools to do that, but it is an extra step. And if you want to update one icon in your sheet, you're going to have to replace the whole asset. It does load the entire atlas into memory, which is bad if you're only using a little bit of it. Now you've kind of wasted a bit of your memory. And there is pretty limited tooling on this available through the Paper 2D plugin. So we have some basic tools for cutting these out and getting the sprite assets, but it is fairly limited. As far as when to use this technique, it's great for things that always appear at the same time. So if you're thinking of like a controller mapping where you have all your button icons, you could throw those into an atlas and assume they're all going to be there at once. If you have some really static HUD elements that are just sort of always on screen, you could throw those in an atlas and draw them in one draw call. It's also great for square or easily packable textures where you're not going to waste too much transparent space within the texture. And as far as how to do this, 3 easy steps. First, you'll create an atlas. There's tools online that can do this. It's pretty easy. You just kind of upload all your images and it'll merge them together for you. Next, you're going to break out sprite assets within the engine itself. So this is right-clicking on the texture that you uploaded and extracting all the sprites, and you'll get a bunch of sprite assets. And then you just assign them to your widgets the same way you would a texture. You can drop them right onto a brush. Won't even tell the difference. And here is how it tested with a little test scene I set up with 64 icons, just to make sure it was working. On the left one, I had it disabled, and it was 69 draw calls to draw my 64 icons, plus a couple labels and buttons I had in the scene. And on the right, with atlasing enabled, it dropped to 6 draw calls. So we can tell it's working there. And this is pretty good when, on some mobile hardware, we're targeting 400 draw calls or so, maybe 500. On lower end, I've heard as low as 100, so this could be critical for squeezing a little bit out. Next up, we have hierarchy design. This is pretty vague, but the idea here is that we are going to come up with smart ways of arranging our widgets in our hierarchy so that we don't accidentally make a bunch of unnecessary draw calls happen based on things being layered. This is also just going to help modify things down the line if you're sharing with other teammates might be working on the same widgets. Make it really easy to read, really easy to reason about how to change things. The pros there, avoiding unnecessary draw calls. We don't want to accidentally draw 3 things that could have been overlapping but aren't as separate draw calls. It's easier to modify if it's laid out well. You'll be able to kind of explain what's going on and won't need to sort of stare at it for a while to see how to change things. And if you've laid things out right, it'll be really reactive to changes in size, screen, resolution, which could be super useful if, for mobile devices especially, you might be supporting a pretty wide variety of screens. So it's worth taking some time to make sure that it's all set up nicely to scale well. The only real con here is that it just kind of takes longer to architect your UI rather than just dragging things onto the screen and going for it. You have to sort of think about how should my panels be laid out, how should things be nested within each other. As far as when to do this, always, because it's just good practice, and there's really no downsides other than it being a little more difficult to set up, but it's good. Here's a little example I kind of set up to demonstrate this. So I made a little fake mini map here with 4 different types of icons. And on the left, I did it in a bad way, where I used an overlay widget and threw a bunch of images in there and used the render transform to set them to different parts of the UI. And that took 21 draw calls, 20 for the icons, 1 for the map. On the right side, I used a canvas panel, and I had everything set to the same Z order, and it did it in 5 draw calls. In the process of doing this, I realized there's this explicit canvas child Z order option. This is a checkbox in your project settings. This will be enabled by default if you created your project with the mobile option, but if you didn't, if you kind of ported to mobile later, it might be disabled, in which case all of these things in this canvas panel are a new draw call. So that is a good thing to check. And just for fun, I threw the 4 icons into an atlas, enabled atlasing, and got it down to 2 draw calls, the map, and all the icons. In terms of just general advice on how to lay out your hierarchy, I kind of have a tree here on the right. You want to size based on the leafmost widget. So try to avoid having constant sizes of things anywhere except at the very, very childmost widget of your UI. And as an example here, we have an image or some text here, which has some fixed size, so like a 50 by 50 image or some text at 16 point. We have that wrapped in a border, which doesn't have a fixed size, but has some fixed amount of padding, so it adds 5 pixels on each side. Those all go into some sort of panel, which is going to have several different children. It's going to add all their sizes together along with its own padding. That's going to go into a user widget, which is sort of how you encapsulate the parts of your UI you want to reuse or that are nice and modular and you want to be able to move around on their own. And that's all going to go onto a canvas, ideally 1 canvas in your project, maybe 2 as a treat. And that is where you're going to anchor things to certain parts of the screen and determine sort of how it all lays out as the screen resizes. In terms of general advice here, limit canvas panel and overlay use, especially be careful with overlays. I see all the time these are in people's hierarchy where they don't need to be. And every child of that overlay is going to be a separate layer, a separate draw call, whether or not it needs to be, because we are assuming this widget exists so that things can be overlaid. So we assume you care about Z order there. Also, just a general pet peeve here, limit your size box and scale box usage as much as you can. It's really tempting to use these things to fix problems, and they sort of inject constant numbers or changes into your UI. There's also risk of things like scale boxes will make everything under them will have to do another pre-pass because after it applies the scale, we have to go and remeasure everything. Obviously, there are times you can't really avoid it, but think about it before you use either of these. Make sure it is the best way to solve your problem. And when possible, use the tree on the right where you're using your childmost widget as your source of truth on what the size of everything else should be. And here's an example of the nameplate widget I made with sort of a good and bad way of doing it. So the top one is a bad hierarchy. I just threw everything into a canvas panel. I put it where it wants to be. The bottom one is a nice, good example where I used horizontal and vertical boxes to package everything together. You'll notice they look identical, which is the idea. The one on the bottom is going to be easier to change and add to because I sort of have containers already built in. It's going to automatically resize as I add things. And it's just a lot easier to work with. And then I don't have any risk of accidentally introducing additional draw calls where I don't need them. And here is a look at the entire HUD that I built. So you can kind of get an idea of how I built different segments here. I anchored them on the canvas panel to different parts of the screen, single canvas panel. I have one more canvas panel for my mini map because it's useful to kind of position things within the coordinate space of some other widget. Otherwise, everything here is self-contained, working off the desired size of its children, its childmost widgets, the images or text that are involved here. So that is hierarchy design. Next, we will go to retainer panels. Retainer panels are very powerful and very dangerous if you don't know how they work. The idea here is that rather than draw a whole bunch of widgets to the screen, we're going to draw all those widgets to a render target, like an intermediary render target, and then we're going to draw that render target to the screen. So the pros here, we can do phased rendering, where you only update certain segments of your UI at each frame. You know, if you're okay with your UI running at a lower frame rate, you could say, all right, do this bit every 4 frames or so. We get this cool side effect where we can apply effect materials, which is UI post-processing essentially. And the entire retainer will draw in one draw call because you've put it all in this intermediary thing. You're basically drawing a picture of your widgets, all already combined. In terms of cons, the biggest one that comes up a lot is there can be some blurriness because we can't pixel snap anymore. By default, we snap widgets to the nearest pixel, so you get nice crisp text. But once you put them in a retainer, we don't know that that's text. It's just a picture of text, essentially. So the whole thing won't be snapped in the same way. There is a memory overhead. You know, we're storing a render target with your whole UI. So especially if it's a bunch of big widgets that are using these, you could end up using a bunch of memory just storing the textures. And if you are constantly redrawing it, it can actually be slower. If you don't use the phased rendering part, then you're just adding an extra step. Now I have to update all my widgets and then draw another thing instead of just drawing them directly. In terms of when you should use this, it's great for UI elements that you don't need to update every frame. If you have some stuff that is pretty static, you could put it in a retainer, or if you have something that you like updates based on player actions but isn't constantly changing, could be a good candidate for a retainer. And then we also see people use it as a UI post-processing tool. So if you want to curve your whole UI or add some blur effect or something like that, it could be useful there. That's not going to help with performance, but it is cool. And here's how I sort of laid out my example UI to demo this. So I broke it into 4 different phases, which are color-coded here. I put my nameplate in one. I put my party panel on the left in another. All the elements at the bottom of the screen in third, and then gave the mini-map its own. So I set these each up to be in their own phase. You know, they all were set to have 4 phases total and then be in one of those 4. And I did some measurements here. So first of all, draw calls, as we expect, are going to drop a lot from 108 to 10 here. That doesn't affect update time necessarily, but we can see that it's working, that we're just drawing these pictures of the UI instead of drawing each widget in its own draw call. And because of the way I phase things out, it was 35% faster. I dropped from 1.2 milliseconds to 0.77. So that was a pretty good performance improvement there. And finally, we have invalidation. So the invalidation system is a way of not updating widgets every single frame, but instead caching some part of their data based on what we can do. We have 2 different ways that we do this. We have global invalidation, where you set a CVAR and it just automatically applies to everything in your scene. We also have a panel that you can wrap stuff in, which applies that same system to a smaller subset of widgets within your hierarchy. That can be useful if turning on global breaks things. You can kind of apply it to the really expensive parts and save yourself a little bit of debugging. In terms of pros here, caching is good. You know, we're doing a lot less work per frame. We can do different types of invalidation. So if it's visibility that changed, or if it's we need to repaint it, or if it changed size, you know, we can invalidate just what we need to. If it changed visuals but didn't change size, we don't need to recalculate the geometry of it. We just need to repaint it. And also, it's super easy to test, especially global invalidation. You just turn on a CVAR and it'll start doing its thing, and you can see, first of all, how much of your UI it breaks. Second of all, how much of a performance improvement you get from it. The cons there, as I said, it can break things. There's a risk of invalidation errors. Anytime something changes, it needs to call the proper invalidate function, which the built-in widgets should do. If you have your own widgets, they may not, depending on how you set them up. So you might have to do some debugging, or it'll kind of show up as stale data. You know, you'll have a timer that isn't moving, or something that just doesn't update when it's supposed to. There is a memory overhead here, because we're caching all this data from the widgets. We're caching their geometry and everything like that. So it will take some extra memory. You probably want to see how much of a footprint that has. And a single bad widget can sort of break the whole system by causing constant invalidation. So if you had a widget that's like really really child-most widget that is changing size every frame, then your whole thing is going to recalculate its whole layout every frame, and it's going to be pretty bad. So you want to kind of keep an eye out and make sure you're not short-circuiting the system. As far as when to use this, performance critical UI is the main time, like a game HUD. In Fortnite, we do not use global invalidation for the front end. We use it for the HUD during gameplay, because it makes sense. We need performance more there. And it's great for large static UI elements, things that aren't invalidating much. You might as well just do all that math once and just keep using it. So keep an eye out for opportunities like that. I know you can't really read these, but I'll point out the important parts. With invalidation off, we had 295 paint calls, and once we turned it on, we had 2. So we're entirely able to work off of the cache data. Now, we're not affecting draw calls here. We're still drawing everything every frame, but we're not doing all the work prior to drawing it. We're using the cache data. And for performance improvement on my test here, it was 90% faster with a huge asterisk, because as I said, this is a static UI, so nothing invalidated ever. But that gives you an idea of your best case scenario. The actual work of painting based on cache data was about 10% of the time it took the UI to update. In reality, your results are going to depend entirely on how much needs to invalidate every frame. So this is one of those things you kind of need to measure in your own project to get a feel for how it's going to go. But there's a best case scenario to work for. It took 0.1 milliseconds to draw everything here. Or sorry, 0.1 seconds. There's also an invalidation debugging tool that you can use. And I kind of mocked up a little visual here to show you how it works. You'll get flashes of color when things invalidate, so that you can get an idea of if something's staying solid pink, then you need to dig into that because it's never caching. Where if something updates and it gets a nice flash, you know that it's working. In order to use this, you're going to launch Pi in a new editor window. So you can't do the in viewport Pi for this because we can't apply invalidation there globally because it's within the editor and it would break the editor. But you can just you don't even need standalone, you can just do a new window and it'll work just fine. You're going to enable global invalidation with CVAR there, enable global invalidation. And then you will start the debugger and you'll start getting these color flashes to tell you what's invalidating, and you'll get different color flashes for different types of invalidation as well. Cool. And with that, I have a couple final random tips to share with you, some good best practices that are worth talking about but didn't really fit in anywhere else. First of all, animations. I didn't really dive into it, but you should expand your animation toolkit. There are 2 main ways that you can do animations in UI. The first is the regular way, the animation panel in the UMG designer. That's going to use sequencer, it's going to drive parameters, it's going to work really well and be easy to use. There is a higher overhead with that. So that's kind of the ideal thing when you want to do one-shot animations that might adjust a lot of different attributes at once, like move a bunch of panels in and off screen, big transitions and things like that. The other technique would be to animate in materials. You can set up reusable materials, you can set up parameters that can be driven by your animations, and you can either animate those still with sequencer, but it's a little lighter weight, or you can animate them directly in the material. This is great for continuous effects, things like a selection highlight, a glowing button, something that runs on a loop forever, doesn't require editing tools in the same way. I've got a QR code here for the UI Material Lab project. This is a really cool project that has 100 usage examples and 40 different material functions. It's on the Epic Games Launcher. I recommend everybody doing UI animation work grab that. You can steal all sorts of cool animations off of it. Some really useful stuff. Another thing that I sometimes see people not really realize quite how it works here. 9 slicing is really cool. It's not really talked about a bunch, but when you are creating borders, panels, things like that, the naive approach would be to just have designer export out a bunch of images. You have a 500 by 500 panel, you get a 500 by 500 texture. You do that for every size you possibly need. Instead of that, you can create a single texture, like a 100 by 100 little square, and you put your borders and your center in there, and we'll automatically tile it all for you. You set up the margins to kind of tell it what part is the border, what part is the center. And you can use the same texture for multiple different panels of different sizes. So in this example, all 3 of these boxes were built off of the same 100 by 100 texture. And that's a single texture in memory. If I need to update it, it's a single texture I need to update, and better in pretty much every way. This is great for resizable boxes and things like that. And I recommend making sure that you are doing this and not bringing in full-size textures that are mostly the same color in the center. And always be reducing your tick count. It is, as I said before, easy to accidentally get 1,000 ticks and have your project slow down a little bit. So you should always be checking in via Slate to make sure that you're not blowing up your tick count, to make sure it's not out of control. You should use the content browser here to figure out what's going on. So a nice little trick with the content browser is if you switch it to column view, we'll show metadata on all of the assets that it is showing. And one of the metadata things we add to widget blueprints is we will have their tick frequency, tick prediction, so an idea of if they'll tick and why they'll tick. So you can see here we have some that are ticking because they have some native code that has a tick function. We have some that are going to tick when an animation plays on demand. And we have some things that just have a tick node in blueprints. So we can find offenders there. We can go take a look at them, see if they should be ticking, why they're ticking, and diagnose some issues. We've been saying this for a long time, but don't use widget property bindings ever. This is the bind button that will kind of be there by default when you open the UMG editor. We have since replaced this with the view model system, and we are kind of phasing out the bindings altogether. The older way to get around this was to do event-based updates. So rather than bind widgets directly to data that you want them to show, you would set up an event node, fire it, update the data yourself. Now you can look into the UMG view model plugin. It is in beta at the moment. It is very powerful. It kind of works the same way as the old bindings, where you have an object with a bunch of data and you bind that data to certain widgets to display it. But it will automatically handle all of the event-based updating. It won't run on tick like the old bindings would. And finally, there are UMG features that you can hide in the project settings. So if you are trying to encourage teams to not use things that shouldn't be used, you can completely disable certain things. You can hide widgets that you don't want people using, which is super useful if you have project-specific button widget or something that replaces one of our default widgets. You should just hide that default. You can disable property bindings so that people don't accidentally use them, or you can make it throw a warning or some sort of error when they are used so that you can fix it. And you can even totally turn off ticking and painting if you are committed enough to try to give that a go, so that people can't accidentally drop a tick node into their widget and start causing CPU cycles to be wasted. And with that, that is all I have for today. Give us a visit at the Dev Hub. I will be there after this talk. We have a bunch of people from the TDR team and from other teams. We have special guests coming by. You can come talk to us about your projects, ask questions, rant about your grievances in the engine. I'm happy to hear all of it. Cool. Well, thank you so much, everybody. Hope you have a great rest of your Unreal Fest.